These are the only 3 trucks that will survive when the grid goes down. And it all comes down to a regulatory loophole that most people have never heard of. While modern vehicles pack sophisticated computers that control everything from fuel injection to transmission shifting, there's a specific cutoff date that separates the survivors from the casualties, and that date is 1996. The Pre-OBD loophole stems from federal legislation that changed everything. In 1996, the OBD2 specification became mandatory for all passenger cars and light trucks under 8,500 pounds in the United States. The Federal Clean Air Act of 1990 required this transition, forcing manufacturers to install sophisticated engine management computers that monitor emissions and performance. But here's what's critical. Anything built before this mandate operates on fundamentally different principles. Before we get into the specific trucks, let's understand why this matters. The U.S. EMP Commission conducted the most comprehensive vehicle testing ever performed, exposing 50 cars manufactured between 1987 and 2002 to electromagnetic pulses up to 50 kilovolts per meter. The results were eye-opening. Only 3 vehicles shut down completely while running, and just 1 refused to restart. Most experienced minor glitches, blinking dashboard lights, radio interference, disrupted turn signals, but remained operational. However, this study had limitations. The Commission had to return the borrowed vehicles undamaged, so they couldn't test to the point of complete electronic destruction. The real-world precedent comes from 1962's Starfish Prime test. When the United States detonated a 1.4 megaton nuclear device 250 miles above the Pacific, the electromagnetic pulse traveled 1,445 kilometers to Hawaii, disabling 300 streetlights and triggering countless burglar alarms. The beta particles literally lit up the sky, while energetic electrons formed artificial radiation belts that disabled a third of low Earth orbit satellites within months. Soviet tests over Kazakhstan that same year, using smaller 300 kiloton weapons, caused reportedly greater damage because they occurred over populated landmass with stronger magnetic fields. These historical examples demonstrate that EMP effects are real, measurable, and devastating to electronics. So, what makes certain trucks immune? It's mechanical simplicity. Vehicles built before widespread computerization rely on mechanical fuel injection, distributors, carburetors, and purely physical systems that electromagnetic pulses simply cannot disrupt. As automotive electronics evolved, vulnerability increased exponentially. The first truck that stands above all others is the Dodge Ram equipped with the 5.9-liter Cummins 12-valve diesel, produced from 1989 to 1998. Tyler from Diesel Power Products describes this engine with a phrase that perfectly captures its essence: too dumb to die. This isn't an insult. It's the highest praise possible for survival scenarios. The 12-valve Cummins represents mechanical perfection. It features a cast iron block and head, forged steel crankshaft and connecting rods, and purely mechanical direct injection. The stroke measures 4.72 inches with a 4.02-inch bore, yielding 359 cubic inches of displacement designed for maximum reliability and longevity. There's no computer controlling anything, just mechanical precision engineering. The fuel injection system tells the real story. Early models from 1989 to 1993 used the Bosch VE rotary pump, while 1994 to 1998 models featured the legendary P7100 inline pump, known affectionately as the P-pump. The P7100 is completely mechanical, featuring 6 plunger and barrel assemblies operated by cam and delivery valves. It requires no electronic timing advancement and gets lubricated and cooled entirely by engine oil. Here's the remarkable part. If equipped with a manual transmission or vacuum-controlled automatic, a 12-valve Cummins requires absolutely zero electrical power to operate. Military variants even included air starters, eliminating the need for electrical systems entirely. You could theoretically build a 5.9 Cummins that runs without a single wire. The second truck is the Ford F-250 or F-350, equipped with either the 6.9-liter or 7.3-liter IDI diesel, produced from 1983 to 1994. These engines predate the electronic complexity that would later define Ford's diesel program. The 6.9-liter IDI debuted in 1983, producing 170 horsepower and 315 pound-feet of torque. Ford increased displacement to 7.3 liters in 1988, bumping output to 185 horsepower and 360 pound-feet. What makes IDI engines exceptional for grid-down scenarios is their mechanical fuel injection system. They require no engine control module or electronics, just 12 volts to disable the fuel shutoff solenoid. Remove that single electrical requirement, and the engine operates purely mechanical. The 7.3 IDI runs a DB2 rotary pump with pencil injectors, 8 glow plugs for cold starting, and a simple mechanical lift pump. The beauty lies in diagnostic simplicity. You can troubleshoot an IDI with a dollar store multimeter and basic wrenches. No scan tools, no computer modules, no complex sensors. It's a truck you can diagnose and repair with fundamental mechanical knowledge. One critical detail separates the best IDI trucks from good ones. Models through 1992 typically paired with the C6 transmission, which operates without computer control. Later models might feature the E4OD transmission, which includes electronic controls that could theoretically be vulnerable to electromagnetic interference. The timing matters crucially here. Ford replaced the IDI with the electronically controlled 7.3-liter Power Stroke in mid-1994. Those later trucks, despite sharing displacement numbers, rely heavily on electronic injection systems that eliminate their EMP resistance. The third truck takes a completely different approach. The Toyota pickup, known globally as the Hilux, with the carbureted 22R engine from 1979 to 1985, proves that survival doesn't require diesel power. These trucks earned legendary status through mechanical simplicity and remarkable durability. The key configuration combines a solid front axle with the carbureted 22R motor. Four-wheel drive became available in 1979, making these trucks capable off-road platforms. The 22R engine displaced 2.4 liters and produced a modest 97 horsepower, but horsepower numbers missed the point entirely. This engine was designed for longevity, not performance. The carburetor represents the critical difference. While later fuel-injected engines require computer control, carburetors operate through pure mechanical and vacuum principles. Air flows through venturi passages, creating vacuum that draws fuel through precisely sized jets. No electronics, no sensors, no computers, just physics and mechanical engineering. Toyota's reputation for reliability amplifies the 22R's survival credentials. Owners routinely report these engines outlasting the rest of the truck. The combination of conservative engineering, quality materials, and mechanical simplicity creates remarkably durable power plants. These trucks have become increasingly valuable as awareness spreads. Classic pre-electronic vehicles have seen significant price increases as preppers and collectors compete for remaining examples. The highest recorded sale reached $60,500 for a 1980 Toyota pickup SR5, demonstrating market recognition of their unique capabilities. But here's what's fascinating about the broader picture. Military vehicles offer additional options worth considering. The M35A2 Deuce and a Half features multi-fuel engines capable of running on diesel, kerosene, motor oil, transmission fluid, and various other combustibles. Commercial utility cargo vehicles, built from Chevy Blazers in the 1970s, often include EMP shielding and military-grade electrical systems. The science supports mechanical simplicity. Vehicle chassis act as partial Faraday cages, providing some protection to internal electronics. However, modern vehicles' increased electronic complexity and interconnected systems create multiple failure points. A single damaged module can disable entire vehicle systems, even if the engine itself remains undamaged. Storage considerations matter too. Smart preparation includes keeping spare alternators, voltage regulators, and electronic ignition components in Faraday cages. These parts can restore functionality to partially damaged vehicles or maintain backup systems. The controversy centers on whether this preparation is necessary. Skeptics argue that EMP-resistant vehicles represent impractical preparation for unlikely scenarios. They point out that if electromagnetic pulse attacks occur, transportation will be the least of our concerns. Food distribution, medical systems, and basic infrastructure would face complete collapse. However, for those living rural lifestyles or depending on vehicular mobility for survival strategies, having transportation that operates independently of grid infrastructure provides invaluable insurance. These three trucks represent the intersection of proven reliability, mechanical simplicity, and electromagnetic immunity. The 1996 OBD2 mandate created an unintentional dividing line between vulnerable and resistant vehicles. Understanding this loophole means recognizing that while the future drives toward ever-increasing electronic sophistication, the past offers mechanical solutions that remain relevant for uncertain times ahead.